Hi! In the second video of this two-part series on the interior of stars, we are diving in a little more deep to figure out the physical processes happening inside the stars. In this video, we will discuss the major equations that determine the fundamental properties of a star and therefore its structure as a function of its radius from the center. So without any further ado, let's begin. In the last video, we ended the discussion on the three modes of energy transport in a star: radiation, convection, and conduction. In radiation, photons carry the energy, while in convection, energy transfers by mass motion of a fluid. In conduction, two surfaces which are in direct contact with each other experience transfer of heat from the hotter to the colder surface. Talking about the fundamental properties of stars, let's begin by one of the obvious ones, that is, its luminosity, which is often proportional to the mass of the star. To determine the total luminosity of a star as a function of radius, let's consider the distribution of an infinitesimal mass dm to the total luminosity capital L of the star. dl is equal to epsilon dm, where the constant of proportionality epsilon is nothing but the total energy released per unit mass per unit time of the material. So obviously, it depends upon gravity, that is the total amount of mass in the star, and the particular kind of nuclear reactions which are taking place in the star. Refer back to one of our earlier videos about these processes. So epsilon is actually a sum of two different constants determined by the total mass of the star and the particular nuclear reactions which are happening inside the star. So now, for a spherically symmetric star, mass of a thin shell will be given by dm equals to 4 pi r square rho dr, where rho is the density of the material in the star. This leads us to the final equation, dl by dr is equal to 4 pi r square rho epsilon. Notice that this change in luminosity per unit radius, the luminosity gradient, depends upon the distance from the center, the density of the material, and epsilon, which is the total energy released per unit mass per unit time in the star. Coming to the next very important property, that is the temperature. Consider, in a stable star, the temperature should not change with time. For the temperature distribution to be constant, the flux entering any layer should be approximately equal to the flux leaving it per unit time. So if radiative transfer dominates in the star, let F of r be the flux of radiation through a surface at a distance r from the center of the star. Using Stefan-Boltzmann law, this tells me that this flux F of r is sigma T to the power 4, T being the temperature of the star. Differentiating this equation, I get dF by dt 4 sigma T cube, where of course the temperature and the flux are both functions of the radius r. Now, if dF of r is a very small change in the total flux due to a small change in temperature T, then we can give this dF of r as 4 sigma T cube dt. But because this change in flux must depend upon the opacity of the layer, kappa, this kappa, which is also a function of radius, is the absorption coefficient per unit mass at radius r, and then kappa into rho, that is the density of the material, is the fraction of radiation which is absorbed per unit length. This leads us to the final equation, that is dF is minus kappa into rho into F dr. The negative sign appears here because the flux is being absorbed. That is, the final flux is less than the initial flux which entered this infinitesimally thin region of thickness dr. Now, if we equate the two expressions for the flux F of r, we get the final temperature gradient dt by dr as the ratio of kappa rho L divided by 16 pi r square sigma T cube. Notice that there is a negative sign on the right hand side. The rate of energy flow therefore depends upon the rate of change of temperature with radius. In general, this temperature gradient dt by dr is negative, which means that the temperature drops with increasing distance from the center of the star. A more rigorous calculation gives a factor of 3 by 64 instead of 1 by 16, which are not very different from each other mathematically. So what does this equation of radiative transfer actually tell us? Well, this equation shows that if the temperature gradient steepens a lot, convection becomes important in a star and hot parcels of matter will move up and the cooler ones will sink down, just like we see in the case of Sun. Convection in stars is not very well understood because it is often very turbulent and requires an understanding of the energy dissipated and the viscosity of the plasma. Our current understanding is that the characteristic convection length scale represented by capital H is proportional to the size of the star. The convection time scale, that is the time taken by a convective element to travel a particular distance, is often equal to the time scale over which structural changes occur in a star. In order to approximate the size of the convective region in a star, consider capital H, also known as the pressure scale height, to be defined such that 1 by H is equal to minus 1 by P dP by dr, where P is the pressure in the star. Now, assuming that the pressure scale height H is a constant, we get a functional form of pressure as P naught e to the power minus r by H. But from equation of hydrostatic equilibrium, we know that dP by dr is minus rho g, where small g represents the acceleration due to gravity in the star. This leads us to the relation that the pressure scale height is given by pressure divided by density into acceleration due to gravity, that is, H is equal to P by rho g. For a typical solar density and average solar pressure, we know that the acceleration due to gravity on an average in the Sun is 550 meters per second. This leads to a pressure scale height of 1 by 4 times the radius of the Sun. A more rigorous calculation will show that the pressure scale height is actually only 1/10 of the radius of the Sun. These simplified calculations lead to a very simplified picture of how and where the convective zones forms in stars of different masses and hence different luminosities, as shown here. However, note that while doing these simplified calculations, we made many of the assumptions such that stars are spherically symmetric, they are static, and stars have no magnetic field. But in reality, none of these conditions apply to real stars. Real stars rotate, and as a consequence, they are slightly flattened at the poles compared to the equator. So to conclude, listed on the left here are the 4 equations which basically sum up the structural properties of a star as a function of its radius. The mass gradient, the pressure gradient, the luminosity gradient, and the equation of radiative transfer of energy respectively. I haven't gone into the details of adiabatic energy transfer or convective energy transfer because they are a little more complicated. I really hope you learned something new in this 2-part series on the physics of the interior of stars. Please do like, share, and subscribe to our channel and share our content with other astronomy enthusiasts. I will see you next week with a new topic in astronomy. Until then, take care.